We'll be starting in 5 minutes. Let's wait for a few more participants to join.
Adit?
Okay, let's start. Hello,
I
everyone.
think we can start.
Okay, yeah.
Go
Hello,
ahead.
everyone. I'm Aditya Parmar, and on behalf of IIITR GRS Student Branch Chapter IIT Roorkee and the Geospatial Engineering Group, Department of Civil Engineering, IIT Roorkee.
Adit,
Yes,
can you turn on your camera?
I
Okay.
warmly welcome you to the third talk of IITR GeoLink Alumni Lecture Series. And we are thrilled to have geospatial enthusiasts joining us today from across the globe to get on the journey of from photogrammetry to neural reconstruction. And about speaker, it's privilege for me to welcome back an alumnus of our department, Dr. Harshit. And Dr. Harshit has completed his PhD in geomatics engineering at IIT Roorkee. And he is currently a postdoctoral researcher at IT University of Copenhagen, Denmark, in an extreme project on extended reality for immersive experience of art and music with expertise in computer vision, photogrammetry, and immersive technologies like Neural Radiance Fields and 3D Gaussian Splatting. His expertise lies at intersection of planetary remote sensing and and decoding the mysteries of the photogrammetry world, and his journey is an inspiration for all of us. And now I will invite Dr. Harshit to begin his talk. Harshit,
Thank
sir?
you, Aditya. Am I audible?
Yes, you are clear.
Thank you for such a warm introduction and very extensive as well. So, hello everyone. So, should I start sharing my screen?
Yes, sir.
Okay. Is it visible to everyone?
Yes, but it's not in the presentation mode.
Now?
Yeah, it's clear now.
Okay. Okay. So, let's begin. First of all, let me introduce myself. I'm Harshit. I'm a postdoc researcher at Data Science section at IT University of Copenhagen, Denmark, as Aditya has already mentioned, in a group that is called Audio-Visual Computing. And from a background perspective, I finished my PhD from IIT Roorkee in 2024 on a topic which is called Implementation of Photogrammetric Point Clouds for 3D GIS Modeling. Prior to that, I also did masters from the same university, and before that, eventually I did my architecture from NIT Patna. So the academic journey for me was a kind of a jumpy ride from architecture to geospatial to photogrammetry. So it's a bit non-conventional way of pursuing something. But anyway, so the group in which I work for now is called AVC, or Audio Visual Computing, where it's an interdisciplinary research group with the cross section of audio, image, video, oralization, extended reality, machine learning, and computer human interactions. The project in which I am currently employed is called Extreme, and the main aim of the project is to basically blending the virtual and physical reality for people to come together for experiencing culture such as art, opera, or other dynamic performances. And it's a EU-funded project which started in January 2024, and it's going to end, I think, this year in 26. We have almost 14 partners across the globe, as you can see in this slide, and it's a very big consortium. So what am I doing in this project? So for starter, my task in this project, because it's a mixed reality project, is to implement or create pipelines where I could generate this 3D, 4D reconstruction using photogrammetry, multi-view geometry, and neural rendering techniques in vision and graphics platforms. So the idea is for me to use photogrammetric experience and computer vision expertise to recognize visual information, and finally generating some sort of computer graphics interpretation of reality. So it's a very not much old, but it's very discrete in its implementation. So this presentation, which I am going to give, would be in three parts. So first, I will talk about the introduction, in which I will give a brief review about the photogrammetric journey I have had, and then we will go into the recent digital representations. And finally, I'll end with the future directions and what I'm currently working on, to be specific. So let's start. So from the reconstruction perspective, we as a human has been trying to reconstruct and recreate our physical world very intensely in form of like maps, drawing, images, measurements. And due to advent of recent technologies, there has been a very diverse expertise and scientific disciplines which are mostly working with reconstructing like terrains building, for example, in geospatial engineering, as I think all of you are familiar with. But there are computer vision as well, where people try to understand how the vision work, how we segment and understand different kind of scene and objects in our surroundings. And in graphics as well, we try to reconstruct those reality to experience in a virtual form. So using images, laser scanners, and satellite observation, these are kind of one of ways in geospatial engineering which we use to reconstruct the digital representation of Earth as well as everything in it. And it's not new, it's very old. So if I talk from the perspective of history, I think Leonardo da Vinci was the first, I think, to use perspective concept to understand the geometry of a scene and reconstruct it in his paintings as well. And this is a snippet from a process of transferring a three-dimensional object on a 2D frame. It's called The Woodcut by Dürer, and it was from the book, The Treatise on Menstruation, and it's basically you can see like it's a 16th century way of doing transferring 3D information into the 2D plane. So it's not new. Apart from that, later on, when photogrammetry became a bit more evolved, so in that we can divide the whole history into four different stages, where the first one was the plane table photogrammetry, where people basically used to have this plane tables and papers and the triangulation principles to transfer the surrounding on a map form of thing. Later in 1900 to 1960, when there was a evolution in imaging and photography, and as well as if I remember correctly, the use of airplanes was very much started at that point of time. Later in 1960s, the whole phase shifted to analytical photogrammetry, in which people use computers, mostly initial stages of computers, to understand the mathematical geometry of scene and reconstructing it as it is. And after 2000s, which is very recent, like 25 years ago, the digital photogrammetry came into picture, where people use this digital imaging techniques, and then representation was again reconstructed into more real looking scenes. And it's also growing recently because evolution of AI, as you have seen in last 3 to 5 years, is booming at its peak. And it's going to be more neural representation as I seen from here on. So how did we do photogrammetry? So the traditional pipeline is when photogrammetry is trying to reconstruct three-dimensional geometry from overlapping images by analyzing the geometric relationship between camera views. So what we do, the typical workflow is we acquire a lot of images from different perspectives of an object, and then we try to understand the poses or the point of view from which those images were captured, which is dealt with camera calibration, in which we try to compute the intrinsic and extrinsic information about the cameras. And we use those pose information to construct a structure from motion of the cameras. So that's what is the sparse information about the whole 3D scene. And then based on those triangulated sparse features, we densified the whole scene by doing the bundle adjustment, and which gives us the whole physical world out of it. And then we can use modeling and texturing to overlay those information about like the color and transparency or something like that. So as an output of photogrammetric reconstruction, we have camera poses, sparse point clouds, dense point clouds, and we can use those point clouds to create polygonal meshes and texture maps. So this is an example which I did in my PhD, where I took some images of our geometric building using UAV, and along the photogrammetric reconstruction, we can actually see like I reconstructed a point cloud of the whole geometric building. So this is what is a point cloud looks like. But not only with the images, we can also add information over these point clouds and integrate it to create more immersive information system. For example, later what I did, I took Apple LiDAR and then I scanned basically the ground and first floor of our building. This was the work which I basically did in my PhD. And then I integrated the point cloud from drone and LiDAR to create this kind of integrated system for the whole building. And from this information, you can actually extract multi-level of details. So it's basically it's a resulted CAD model from the point cloud, which I showed you earlier. And later on, because I'm talking with the geospatial community, so we can add our geospatial information as well over this to create a 3D GIS model. So what exactly is a 3D GIS model? So the model, which is 3D, it doesn't have any information about its topological spatial relationship. So it doesn't know exactly the information about, like, suppose how many doors are there, or what is the volume of wall, or how many windows are there, or how many solar panels are there on the roof and everything. So from a geospatial perspective, you can add on this information using like segmentation and some machine learning techniques, which could be useful for, suppose, creating an indoor navigation system, or creating a kind of a system of information stored for a future use cases. So for photogrammetry, what works well is basically it gives us very high geometric accuracy. And because it's not a new field, it's a very old field, so there has been a lot of development from the mathematical point of view. So it has very well established mathematical foundations, and it could be scalable for like one building or multiple buildings, or for a city as well. And it has a very good compatibility with GIS and CAD systems, so we could use it in various scenarios, various systems. And that's provide photogrammetry strength for its use cases in topographic mapping, urban modeling, cultural heritage documentation, and infrastructure monitoring. But it does not change during image capture, because once you capture the image, you have the snapshot of the time. You don't have anything in the time. So this assumption kind of limits photogrammetry in several ways. For example, like if there's a moving object, it can cause reconstruction artifacts. If there are temporal. So the next part is another domain, or it's a new representation of reality, I would say, where we would try to understand how this new representations could be useful for capturing the dynamic scene. So, for example, how do computers see the world? So, as we have seen, like the information in our last few slides, point clouds are one of the most basic way we use to represent 3D shapes, like the collection of dots. And some of the better representations are called voxels or polygonal meshes, which is also how we see or how we store our information in computer. And but if we start to question like how camera sees the world, so it doesn't have a geometric analysis system, or it doesn't have any other information, because if we see from the camera perspective, it just takes or captures the light rays in form of some signals, which signals are basically now converted into bits and pieces, which is basically reconstituted in form of the pixel value or the digital number value in form of our images. So what if we could use this intensity of life and the direction directly for recreating the reality or reconstructing the 3D scene? So as a comparison, traditional photogrammetry mostly interpreted as a geometric observation, but physical perspective is camera only measures light. So this is one key principle which we will use in further slides to understand how this could be really good for reconstructing reality. So in 1991, Adelson and Bergen, in their work, which is called The Planoptic Function and Elements of Early Vision, they attempted to answer a question, which was like, what information about the world is contained in the light filling a region of space? So just imagine your whole world is made of a lot of small volumes or of spaces. And what if we could map everything in that 3D space in the perspective of light? So that is what it is called planoptic function, in which you try to find a function that can define the whole 3D reality from the perspective of a 3D space, a radiance, wavelength of light in that 3D space, as well as time. So you can see the function here is like P is a function of the 3D view locations with the angle from which it is viewing, and it's adding the lambda, which is the kind of radiance information with the time. So you can, if you have this kind of function, which is kind of a 7 to 8 dimensional function, so you can theoretically map or reconstruct the whole reality around you without even constraining time or any other color information. So this is what was called planoptic function. And this is kind of a basic basis on which the other interpretations has been evolved. Based on the planoptic function, there is other research which is prior to the planoptic function, which was in Arun Gerson's classic 1936 paper, where they defined light field. And light field is a kind of an interpretation where you have this intermediate or memory efficient format for storing and synthesizing 3D scenes. So multiplane image is one form of this light field interpretation. So you just imagine like each subject or each object in a scene based on the depth is stored in different layers. And if you overlay those different layers, you can have a kind of a three-dimensional interpretation or representation of the whole scene. And this is one of the concepts which is also, I think, has been used in Disney movies, where you have like this multi-levels of characters moving, and then you shoot the camera through those layers to basically capture the three-dimensional or the depth of the whole scene in moving picture. Yeah, so this was one concept. And then recently, another idea which has came as a revolution, especially in the computer vision and graphics world, it's called the radiance field. So radiance field is kind of a mathematical representation and also a part of planoptic function, where we try to describe how light radiates through 3D scene, specifying the intensity and color of light traveling in every direction. So remember the planoptic function where we try to basically map everything in every direction from every point of view. So the same idea is used in Radiance field, but we don't have for now the time parameter, and we don't have for now the wavelength parameter or the electromagnetic radiation parameter for mapping the field, but we have the color and the direction. And this representation is basically rendered using volume rendering, and it's also called as implicit representation of the field, because you don't have a discretized way of representing a scene. So what you have, you give a location of a point, and from point in which direction that point is looking, and then the function could give you the color, which is RGB, and the opacity. So this is in a nutshell the radiance field concept, which is being used recently. So all of these ideas which we discussed earlier is a form of neural scene representation. So if you try to generalize it in a way, so we could say the neural scene representation is a way to encode the 3D scene using like geometry and appearance inside a neural network or a learned structure, so we can render images, reconstruct geometry, simulate views from any arbitrary camera points. So it's a very interesting idea. Like you just capture like few observation from sparse viewpoints, and then you can create the whole volume, which could be looked from any perspective, from any point of view. So this is a kind of a recent paper which came from Google DeepMind, where you can see you can use this 3 different views to construct information, which is a kind of a representation network, which will give a kind of a scene representation. And based on those representation, you can train the model to create a kind of a generation network where you can query any viewpoint, and you can compare that to make it more like rectify the whole pipeline. So now we are, so the radiance field idea, which we discussed earlier from a mathematical perspective, recently there has been this research which came in, I think, 2020, which is called, I think, NERF, which is Neural Radiance Field, which is a very influential method of mapping the radiance field of a 3D scene. And what it does is basically it generates the rays along the 3D scene, and it tries to map each point along that ray. So what you see on this A side of the image, so you have this 5D input, the position direction, where you have this direction of a ray, and then you map each point on that ray, and then you provide a function which could be able to extract the value for RGB and opacity for each of those rays. So if you see, like whenever the ray is hitting this subject or object in the 3D environment, it's giving it the value of the color and opacity of that area. So it's a principle which is also a bit old, which was also called volume rendering, in which you try to render the each volumetric voxels of the whole scene. And through that, you try to compute the rendering loss, and that's how you train the model. So imagine we want to render this triangle and this square from this volume rendering perspective. So what does it do? Like it starts with a random kind of a scene or representation in which you can see this blue smudgy representation which is coming out of this first 350 iteration, in which you map all this rays and you give these rays the information from the respective images, and then you try to in what it is called, you try to minimize the loss of this information of color with respect to the ground truth images. And after like 650 and 2500 iterations, you can see it's kind of getting the shape of the input images. So this is what volume rendering is about. It tries to render the each volume along the ray in a 3D environment. So in a nutshell, what NERF does is basically using that volume rendering principle and multiple images, it reconstructs the whole reality, which is also called novel view synthesis from other perspective. But the limitation of NERF is it's computationally very expensive, because imagine you have to like render a whole volume which doesn't have any information about any light, because a lot of our 3D environment is just air, it's just space, it doesn't have any other information other than that. So it's really computationally expensive in that way, and it uses neural networks, so it's also slow to render. So that's kind of one limitation for the NERF. So recently, after the NERF paper in 2023, there was a new discovery, which is called the 3D Gaussian Splatting, which is another Gaussian-based representation in which you model a three-dimensional scene based on the Gaussian primitives. And this again goes back to that 1991 paper where the author wants to try to reconstruct the reality based on some of the primitive objects. So in NERF, as we have seen, we have to map like for each pixels or each points along the rays. For Gaussian, what we do, we just take a kind of a sparse structure of a scene, and we replace those sparse structure of the scene from a Gaussian ellipsoids. And then we use those 3D Gaussian ellipsoid to splat on a 2D screen, and then we compute the loss between the splatted version of the image and the ground truth, and then we try to improve the accuracy of the representation. So if you go into the details, so just imagine a Gaussian is just a distribution which could be described as a bell curve. So if suppose we want to represent this triangle from a three Gaussian perspective, so this is a kind of image which we get. So it's kind of trying three basically Gaussian primitive to try to generate this kind of triangular representation of the scene. And if we increase the number of Gaussians, so it will become something like this. So on the left, you have like the original triangle. Then in the middle, you have like three Gaussians representing the same shape. And on the right hand side, you have like 20 Gaussians trying to fit the presentation or appearance of the triangle. So that was 2D. What about 3D? So for 3D, we have this equations, which is an exponential equation for Gaussian, where you define a 3D Gaussian in a space based on its mean location, which is kind of the center position of the Gaussian. And then you have this covariance, which is defining the shape, which is like scale and rotation and how spread it is in the 3D. And you have then color and opacity. So this is how you define a 3D Gaussian in a 3D space. And if you are able to run it, like train it or maybe compute it efficiently, so this is kind of a result you can get from like 50 or 60 images of a 3D scene in form of a Gaussian splatting representation. So you have a 3D Gaussian, and then you convert that into 3D ellipsoid. But what about the covariance? So the covariance is basically broken down into two information system, which is like the rotation and scale. Because if you imagine the rotation parameter and scale parameters are kind of the description which could be derived from the camera intrinsic pose information. And using those information, you can actually then reiterate the whole sequence of this thing to either make the Gaussian longer or smaller or larger, something like that. So for example, this is a kind of a covariance matrix using eigenvalue and eigenvector. So the eigenvalues are used to represent this ellipsoid principal axis, and the vectors are providing the orientation of 3D space. So this is how this Gaussian splatting works. And the main contribution of the paper was basically the differential rendering. So what exactly differential rendering is? Like suppose you have this millions and millions of Gaussians, and you can actually use those all Gaussians because you're just trying to splat them and compute the loss between the images to improve the accuracy of the appearance. You can do this by uh, GPU coding or basically parallelizing the whole sequence. So you don't need to basically overheat the whole CPU. You can actually parallelize the whole system, and that's what differential rendering is about. You render the whole sequence in form of small differentiable members. And that's what it's remarkable, and that's what makes it real time, uh, gives it real time's capability. So the whole process is basically you have this structure from motion point clouds, which could be generated from either Colmap or some open source softwares. And you transform these points into form of some random 3D Gaussians. And then you use adaptive density control, which is a kind of a way to project and control the density based on the information it is trying to fit. So suppose you have this kind of shape you want to show, and you have this Gaussians, which is basically undersampling the whole reconstruction. So what adaptive density control does, it basically, okay, let's clone this Gaussians to fill up this space, and then it tries to again optimize the whole situations. And the similar way, if you have some bigger Gaussians, you try to split and optimize. So this adaptive density control is the key to making this whole Gaussian workflow fit to a general representation. So this is kind of an output of rendered image. And if you see, if you turn on the 3D Gaussians on the background, so this is how it looks in the form of ellipsoids. So you can see these are like a lot of ellipsoids across the whole scene, which is trying to make sense or create a kind of realistic viewpoint. And this is how you can, this is the result, which is like very famous from the NERF paper by Kerb et al. And another very important point I wanted to note is like using through Gaussian splatting, you can actually have the view dependency effects. So if you see here, if you change the view, the color and the orientation of the Gaussian changes, and that gives you this very remarkable way of visualizing this different scenario of a single scene, which kind of a little bit gives you a dynamic sense of the whole scene. So this is very interesting, and this is what is done in Gaussian splatting using spherical harmonics interpretation, where you try to map all this color and opacity based on this different levels of spherical harmonics. So why does it works so well? So the real reason is because it has this very fast rendering capability, and that makes it real-time performance available. And it basically opens a lot of different applications, especially in autonomous driving, SLAM, and even digital twin in robotics. So in a nutshell, 3D.js is basically provides us a very fast rendering speed because of the differential rendering, because we're not storing a lot of 3D points. So it is very efficient in storage. And because of the spherical harmonics, it has this continuous representation. So if you change the view, you can actually have this view changing effects on different scenes. And that's what it gives the high visual realism. So that's why they are the richer description of the real environments and its combination of small radiance elements. Okay, so that was the neural part. And now let's move on to this future research direction in which I'm trying to currently work on, which is the dynamic scenes. So from the point of view of dynamic reconstruction, it's kind of the similar approach from the normal 3D reconstruction, but with an addition of time. So we use, again, what I'm currently using is the multi-camera input to compute the camera poses. And then I'm generating a 3D dense model, which I'm converting into this neural representations. The part which is interesting is the temporal analysis, because if you have a scene which is changing along the time, how you record the whole performance in that way. So the idea I'm currently using is basically to have a spatio-temporal feature along the four dimension and trying to reconstruct that feature into the whole 4D representations. But there are lots of challenges in that, because you have to have a representation that has a dense structure, and it's a very because you are dealing with the time, so you have to have this temporal coherence and a very compact storage systems, because you have to have like millions and millions of points along the time as well as along the spatial dimensions. And because of this, it is really tricky for now. And but yeah, lots of research uh, groups are now developing on this, around this field. And as physical world is dynamic, so we can reconstruct some representation in that way. So this is a kind of a neural radiance field based representation of a scene, on a dynamic scene, in which we basically we try to use the deformation field across the whole information of the time. And this is another data set which is also available, which was work of I think CMU Planoptic group, and they have this like 30 plus cameras, and they use this whole set of information to reconstruct this Gaussian representation in dynamic. But the problem is, like, if you have this very huge volume of info of the whole information, so it's really tricky to uh, solve this from the compute perspective. So the idea I was wanted to give from this talk was like, this is one of the field I'm looking forward, especially from the geospatial perspective, because the work I'm currently doing is not totally geospatial oriented. So I just wanted to give a kind of a the idea that how this neural scene representation and this four-dimensional modeling could be used in geospatial engineering. So especially from the point of view of digital twin, suppose this dynamic reconstruction could actually be the foundation for the future digital twins, because it would be able to enable us from the continuous monitoring and interactive visualization with the predictive simulations. And it's really interesting to see forward a lot of research in this field. And apart from this, there's lots of future research areas because of this integration from photogrammetry and neural scene representation. Like, I would like to recommend for especially the young researchers and the students who wants to work in this kind of integration of photogrammetry, computer vision, graphics, and neural representation. You have this dynamic photogrammetry, which is coming recently. Another is neural geospatial models, where you can represent radiance-based model in geospatial data structures. You have real-time reconstructions. 4D geospatial database, one of the very crucial domain of research, because you have to now deal with a way more volume of data as compared to the 3D world. So these are some of the research areas I would recommend for young researchers to work on. And just to conclude, the key message on the vision I wanted to pursue was, as photogrammetry has enabled us with the geometric modeling, which is very accurate, but still there is a component of static snapshots of reality. So using neural scene representation in that way to kind of create a new possibility for representing appearance, motion, and temporal evaluation, we can actually integrate these two to move forward. And I'm pretty sure that we might move from the measuring the world, which is a kind of a key role in geospatial engineering, to more simulating and manipulating the world, which will be a kind of a open opportunity for the research and innovation in geospatial engineering. But I would skeptically say that it's a very long journey ahead. So I think the research needs to be done very crucially. So I think that's it from my side. Thank you everyone for listening. I hope I have covered a basic idea of how the photogrammetry has evolved into this neural scene representation, and how this could be integrated to pursue in the future for 4D reconstruction and dynamic modeling of our environment. So thank you everyone for listening. I will hope if you have any questions, you can pose.
Yeah, Aditya, we can start Q&A session.
Yes, thank you, Dr. Harshit, for like a very good explanation, like how we are moving from photogrammetry to like neural scene representation. And we are also up for question, but I want to ask the question first.
Okay.
Like currently we have like Tesla cars and some robots who are like navigating in the real world, and
Mm-hmm.
they are like constantly like taking information, creating 3D models, and taking decision based on that. So what does like how dynamic photogrammetry and neural scene representation will like change this current thing of
Okay.
3D?
Okay. So, okay, that's a good question. So, what I see is the information which you are mentioning from the Tesla car and this other Waymo is also one which is trying to uh, reconstruct the reality. So it's very specific for a application point of view. So it's trying to reconstruct the reality on roads, and it's basically taking the decisions on the basis of that. But from the perspective of neural scene representation and photogrammetric reconstruction, what I would like to see in the future is to have a richer representation of the reality. And the richer representation I'm mentioning is from a perspective of like geometry and appearance. So it's like how we can have a world inside a world. Like, and it's basically comes from an idea like how we as a human perceive a reality. So it's more in a direction of understanding your our own vision and perspective of reality using this reconstruction and representation system, ra- and like creating this richer experiences. Because as currently I'm working in this immersive technologies, so the more immersive you are in a scene using a VR goggle or something which is giving this you notion, so the more we can actually look for the glitches. Because in the 3D physical environment, it's almost like the way we see, the way we interpret, it's very like dense in information. But if you try to reconstruct that in a immersive reality, and even if you have like a little bit of gap or loopholes or something like that, it creates this kind of glitch in that experience. So then we come to know or appreciate our own understanding of the 3D reality. Like, oh, like we are as a human, we are like so hyper perceiver in that sense to understand our reality. Like we take it for granted. So for virtual reality, and especially in the immersive technologies, if we try to uh, perceive anything, we have to have a richer experience. So for that kind of things, we need to have this neural scene representation and photogrammetric reconstruction in that sense. So I think, in a nutshell, just to answer your question, like I see it to be become more real, more dynamic in a sense that we would be able to not understand the difference between the physical and the virtual world. That's my
Okay,
aim is to be, yeah.
okay, thank you.
I hope
Any
I
other
answered the
question?
question.
Anyone else?
I
Yeah.
think I've shared a lot of information for people to wrap around.
So if we done with the Q&A session, so we can conclude the lecture.
Okay.
So thank
It
you,
was an
sir.
honor for me to present. And if anybody of you want to like know more about this or learn more about this, you can write to me or email or anything. So I'm always open for uh,
Yeah,
learning new things about new world. So thank you
definitely, sir.
for this opportunity.
So on the behalf of IEEE GIS student branch chapter, I would like to extend my sincere gratitude to our alumni and distinguished speaker, Dr. Harshit, for delivering such a insightful lecture on from photogrammetry to neural science, neural scene reconstruction. Your talk highlighted lots of things like 3D Gaussian Splatting, neural radiance field, and cutting edge technology that is like very helpful for a representing our real world through the photogrammetry. So it's very insightful lecture for us and for our audience also. And I also deeply appreciate the participants who join us today. Uh, as the number of participants always increase our effort that we are putting to frequently organize these lectures. So yeah, so we look forward for next session, or maybe we can say the next series lecture, next lecture in this series. So yeah, thank you, sir, for
Thank you.
connecting with us, and we hope we will connect in future event also.
Surely. Thank you. Thank you for the opportunity.
And yeah, and all the lecture recorded in this series will be available in YouTube. So if anyone missed anything, so they can recap from there also.
Thank you.
Thank you, sir.
Bye-bye.
Thank you, sir. Bye bye.
Thank you. Bye-bye.